Most RAG failures are query failures. By the end of this video, you will understand how simple query rewriting and a small HyDE-style trick can turn misses into hits and boost recall without changing your index. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Query rewriting for RAG recall answers a practical problem. You ask a question, and your retriever returns the wrong documents. The documents you need are in the index, but the question uses different words. That mismatch is the common failure mode. Engineers reach for query rewriting to reformulate the question so the retriever sees more overlap. Success looks like more correct top hits, fewer downstream hallucinations, and no expensive reindexing. At a high level, rewriting means generate alternate phrasings of the same intent. You try synonyms, expanded forms, or even a short hypothetical answer to change token overlap. This trades a little extra compute for much better recall. It is cheap compared to rebuilding embeddings or swapping models. The weakness is cost and noise. More rewrites can also surface false positives if you are not careful. We will build a tiny toy pipeline to show the full idea. First, we make a simple lexical retriever to expose the problem. Then, we wrap it into a reusable function. Next, we generate multiple rewrites and fuse their hits. After that, we create a short hypothetical answer to bias ranking towards semantic matches. Finally, we measure recall gain. The code is minimalist, so the behavior is obvious before you map it to a larger system. Now, we will build a tiny lexical retriever and show how brittle exact matching can be. This snippet builds a tiny lexical retriever and shows its top hit. It defines the list docs as a miniature corpus and the function toke to tokenize text into lowercase word sets. The variable q holds a natural language question. The list stores pairs of overlap score and document index by intersecting toke of q with toke of each document to count shared tokens. Sorting S by descending score and then by index makes the result deterministic, even when scores tie. Finally, the print shows which document index ranks first under this naive overlap strategy. Seeing the index highlights how brittle exact term matching can be when vocabulary differs. Next, we will wrap that behavior into a reusable retriever function so we can test different settings. This example turns the baseline into a reusable top K retrieval function. The function retrieve takes a query and returns the top K document indices by computing the same token set overlap with each document and sorting by score, then by index for stability. The variable res holds the top two documents for the earlier question, showing which items the simple lexical pass considers most relevant. Increasing K broadens recall by admitting more candidates for downstream fusion, but costs more processing. Decreasing K tightens precision and can hide valid answers. The printed list confirms which entries the lexical baseline would hand to the next stage. Next, we will generate several alternate phrasings of the question and fuse their retrieval results. This code implements multi-query rewriting and fuses results for a strict top 1 check. The function mqr returns 3 formulations of the question, swapping in terms like PV cells and photovoltaic to mirror how the corpus might be written. The variable base stores the top 1 baseline index from the original query. The list SC computes, for each document, the maximum overlap score across all rewrites, which captures hits missed by the original wording, because one rewrite may match different document tokens. After sorting by that fused score and then index, the code compares whether document 1 is retrieved under fusion but not under the baseline. The expression delta flags when rewriting turned a miss into a hit, showing immediate recall improvement without changing the index. Now we will augment rewrites with a short hypothetical answer to bias ranking toward relevant content. This snippet adds HyDE-style hypothetical text to bias ranking toward better semantic overlap. The function HyDE produces a concise, likely answer text from the question so that documents that match the expected answer get extra weight. The function hybrid retrieve computes the multi-query maximum score as before, but also computes overlap with the HyDE text and adds half weight for that overlap. So documents that align with the hypothetical explanation receive a boost. Sorting the combined score stabilizes the order, and returning the top K completes the re-ranking. Increasing K broadens candidate coverage. Increasing the 0.5 weight would favor HyDE tokens more strongly. The printed index shows the HyDE boosted top 1, which often corrects lexical misses. Finally, we will quantify whether these tricks actually help on a tiny test set. This example measures recall gain at top 1 using the hybrid approach. The list QS holds 2 queries with ground truth document indices 1 and 2 zipped alongside. The variable B counts baseline hits using the reusable retrieve function at k equals 1, which makes misses visible in a simple way. The variable F counts hits using hybrid retrieve that fuses multi-query rewriting and HyDE-weighted overlap. The variable gain computes the difference between hybrid and baseline recall fractions, so we see the immediate uplift. A larger gain means the rewriting strategy is paying off right away. The printed value confirms a measurable improvement in retrieval quality without changing the index. Mapping this toy flow to a real system is straightforward. Replace the tiny lexical overlap with TF IDF or sparse embeddings. Keep the same rewrite and HyDE logic, and use these steps as a re-ranker in front of your reader. The small extra compute is often far cheaper than re-embedding or changing the index. Recap. Query rewriting means reformulating the question to expose matches the retriever missed. Use multi-rewriting and a short hypothetical answer when the index has relevant documents but lexical mismatch hurts recall. Caveat. Too many or noisy rewrites can introduce false positives and cost more compute. Next step. Tune the HyDE weight and the top K together to find the sweet spot between recall and precision for your corpus. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.